Here at ARDA Power, we have designed a microgrid solution that not only delivers the many benefits of a microgrid, but is also easy to understand and implement. Building owners and tenants are now considering microgrids for a diverse set of reasons: a desire for more resiliency, for increased utilization of renewable energy, or as a hedge against inflation in energy costs. But they are frequently held back or put off entirely by the complexity of currently available alternatives. The ARDA DC microgrid platform makes possible a modular microgrid solution that addresses concerns about the complexity and costs of implementing a microgrid. While ARDA, together with partners, can provide customers with a turnkey solution and support throughout the design and implementation phase, it is useful to understand how the modular components are used together to create a microgrid. So let's take a close look at one example, how an ARDA microgrid is implemented in a typical commercial building. A typical building electrical configuration consists of various AC loads connected to a breaker panel that is in turn connected to the grid. Any DC loads, like computers or LED lights, require electronics to convert AC energy into DC energy. When the grid goes down, so do all of the loads. If on-site backup generation is available, costly components, including static switches, are required to maintain power. Before implementing a microgrid to address these and other concerns, we recommend that you consider energy efficiency measures, including upgrading to high-efficiency devices, frequently DC, including those for lighting, air conditioning, and refrigeration. For example, since LED lights reduce energy consumption by 70 to 80% as compared to incandescent lights, they proportionally reduce the size of local generation and storage assets required for lighting. By doing this, owners and tenants can make it significantly less costly to implement a microgrid. Let's get started now with the typical implementation. First, local generation sources and storage, if they don't already exist, are installed on site. A common anchor for a building microgrid is a rooftop solar plant, shown in green, to provide peak energy. While intermittent, solar generation typically peaks in parallel with consumption on hot, sunny days, reducing energy requirements and capacity charges. The PV plant is connected to the microgrid using low-cost DC-DC converters, shown in red, for instance a solar optimizer, via a common DC bus. To provide a non-intermittent source of local energy, we next add a high-efficiency variable RPM gas generator, shown in green, that can be connected directly to the same DC bus. These high-efficiency generators save energy and money, reduce emissions, and if connected directly to the DC bus, will cost less since an internal inverter will be removed. After our generation sources are in place, we add a storage source, shown in green. For instance, a flow battery to provide long-duration storage that is connected to the same DC bus using an ARDA battery DC-DC converter, shown in red. The ARDA battery DC-DC converter contains a distributed virtual microgrid controller that manages power and energy, maintains DC bus voltage, and uses the DC bus to communicate with sources and loads. This eliminates the requirement for a separate wired or wireless network. After any new energy sources or storage devices are in place, one or more AC breaker panels are removed, and a new smart DC breaker panel, shown in red, is installed in its place, connected to the common DC bus, to which the generation sources and storage are also connected, in many cases using the same wiring as the AC breaker that was removed. Next, any new or existing DC loads, like LED lights or VFD-driven loads like high-efficiency HVAC systems, are connected or reconnected to the smart DC breaker panel and become uninterruptible. That is, they will continue to operate with no latency when the grid goes down. The smart DC breaker panel handles ground fault detection as well as certain load management functions. Finally, a stripped-down low-cost grid tie inverter is installed to handle the import and export of energy, as well as the provision of ancillary grid services, including frequency regulation or demand response. AC loads remain connected to the grid as before. You now have a fully functioning microgrid, including local generation, storage, and select DC loads. As you will see later, we can also add AC loads to the microgrid. All at low cost, using modular components, with an easier interconnect application, no separate communications, and minimal or no custom engineering. And because of this configuration, you don't have reactive power flows or frequency synchronization requirements, and you don't have to install bulky and very expensive static switches. Since the system is modular, future additions are possible without re-engineering. For example, you can expand the solar plant using additional low-cost DC-DC converters connected to the same or an additional smart DC breaker panel, or add a second local generation source like wind, or additional storage such as a lithium-ion battery. With or without the increased local generation capacity and storage, you can add an ultra-low-cost DC-AC loads inverter, shown in red, to support uninterruptible AC loads on the same microgrid, expanding the scope of the implementation. At a later date, or immediately if you prefer, you can replace those uninterruptible AC loads with high-efficiency DC loads, adding to or expanding the existing smart DC breaker panel, and removing the requirement for a DC-AC loads inverter altogether. Now you understand the basics of the ARDA microgrid solution, including how various modular components and controls are used to create a complete microgrid. But this is not just a theory, this is a reality. So let's take a look at a real-world application. A solar plant, a gas generator, a 5-hour flow battery, a grid tie inverter, new high-efficiency LED lights, DC refrigeration, and air conditioning, all connected into a single microgrid with modular components and no custom engineering. Operating in a commercial industrial building in Burlington, Ontario, connected to the local Burlington Hydro utility grid, capable of off-grid operation and the provision of ancillary services. With a flow battery provided by Gildemeister Energy Solutions, gas generation provided by Polar Power, LED lights provided by Nemalux, and funding provided in part by Sustainable Development Technology Canada. For more information, check out the project's blog on our website. Welcome to the dawn of the plug-and-play microgrid.